Hello everyone. In this video, we will be discussing about SN diagram, its experimental setup, and all the related graphs to this fatigue. So, fatigue strength of a material is determined by R.R. Moody rotating beam machine. He is the person who invented this particular machine, and through this machine only we are doing all this fatigue calculations and the graphs, whatever. The surface is polished in the axial direction and a constant bending load is applied. You can able to see in the sketch a typical testing apparatus is there. I will explain you very quickly. So what are the major components are there? You can able to see this. There is a motor and this motor is connected to a specimen. You can able to see this specimen is fixed in both the ends in such a way that it acts like a simply supported beam. And the specimen usually recommended one is the circular cross section specimen. And since it is a simply supported beam, intentionally a load has been hanged in the center of this particular specimen so that it makes the body to bend. Simultaneously, on the right side of the machine, we have uh, something called a tachometer kind of thing. So, what is the purpose of this virtual tachometer? Is it will measure and it will show the count or the rotation which the specimen is going under. So, with the help of this motor only, I will be making this particular shaft to rotate. So, the shaft will be rotating, and already there is a bending load which is fixed on the specimen. So, it is going under torsion and simultaneously it is going under bending. So all this rotation has been recorded by using a tachometer which is fixed on the other side. Here the speed of the specimen can be increased depends on the motor capacity. If I want to increase the speed of 100 rpm, 150 rpm, 200 rpm, even if I want to reduce to 50 rpm, 30 rpm, anything is possible based on, because we will be selecting the motor in such a way that it is supporting the specimen to rotate in the required speed. And these kind of what is this particular apparatus, ultimately we will be getting a fully reverse stress cycle. We know what you mean by fully reverse stress cycle, where the mean stress value equal to 0, and there will be a equal stress amplitude in all the stress in the all the like stress cycles. So that is the unique nature of this reverse bending stress cycle. And here you can able to see a record is kept of the number of cycles required to produce failure at a given stress, and the results are plotted in a stress cycle which is shown in the sketch. A little consideration will show that if the stress is kept below a certain value, the material will not fail whatever may be the number of cycles. This stress, as represented by the dotted line, is known as endurance or fatigue limit. It is defined as the maximum value of completely reversed bending stress which a polished standard specimen can withstand without failure for infinite number of cycles, usually 10 power 7 cycles. It is not 1077, it is 10 power 7 cycles. Let us have a look on this particular graph. You can able to see this. What is this x-axis means the number of cycles, like 0, 100, 1000, 10,000. We can able to see 10, 100,000, 10,000, 1 lakh, 10 lakh, and 1 crore. So all those things we can able to see this. And here even the y-axis is all about this y-axis is all about the failure value, that is the stress value, the stress factor value. You can able to see starting from 30, 40, 50, 60. You can able to see when the material is going under the repeated stress cycle, that is the rotation. What is happening means you can able to see there is a reduction of the stress value. It means like the material quality is going under, and this is very natural almost for all the material. And this phase, that is starting from one cycle, that is zero cycle to the 1000 cycle, you can able to see there is a gradual reduction of the the material fatigue because of the heavy tiredness. And later also we can able to see, starting from 1000 to the 10 lakhs, again there will be a gradual decrease in the material failure thing. It may, at any point it may lead to the failure, and all these scattered points indicates the different stress points for the different materials. And after 10.6 or 10.7 you can able to see this, there is a straight, there is a constant line. So what is the meaning of this one? Means for the different materials, of course, what is the meaning is, once a material can able to successfully rotate till the 10 power 7 cycle, then we will be calling that as an infinite a tireless material, which will not have a failure due to the tiredness, that is due to the fatigue. So these different dots are different materials. If you see means, and this particular graph is plotted on a semi-logarithmic sheet. We know like all these technical graph points and all will be plotted only on the semi-logarithmic sheet. So based on this graph only, we will be identifying whether it is going which material is coming under low cycle category, and which material is coming under high cycle category, and which material is having an infinite life. That is very very important. When your material is successfully completing this 10 power 7 cycles, means then that material need not be taken for any kind of the fatigue test, because already it is proved that the material is having a capacity to withstand any kind of failures. And in this, it is connected with the fluctuating stresses. That is, the failure points from the fatigue test made with different steels, and the combination of the mean and the variable stresses are also plotted in the figures as the function of the stress amplitude and the mean stress. The most significant observation is that in general the failure point is a little related to the mean stress when it is compressive, but it is a very much function of a mean stress when it is tensile. Everyone have to remember this one. The failure point is a little related to the mean stress when it is compressive, but they very much function of the mean stress when it is tense. And you can able to see this, how an axial load, whether it is a tensile load, means it is very much mean to the function, but if it is a compressed stress, means it is very much related to the failure point. And in practice, this means that the fatigue failures are rare when the mean stress is compressive or negative. So a material which we are talking about, it is going under the compressive load, means we can say like the failure chances are very very less. Therefore, the greater emphasis must be given to the combination of the variable stress and the study, or even will be called it the mean or tensile stress. Here you can able to see the different like fatigue points for the different engineering materials which is recommended. Mean stress and versus alternating stresses. We have a Soderberg line, we have a Goodman line, we have a Gerber line, and this particular line is the yield line. You can able to see Soderberg line, it is for the ductile material, Goodman curve for the brittle material, Gerber curve, it's fully scattered points, it is for the composite materials. All these things was finalized based on this yield line only. So when it's hereafter in any problems or any concept, if I particularly speak about ductile material means, then immediately I need to think about Soderberg failure line. Or else if I am particularly focusing about the ultimate that is the brittle material means, then I need to immediately talk about the Goodman failure line. And if it is a composite material means, then I need to see the graph of the Gerber curve. So in the upcoming video, we will be discussing this the combination of all these stresses like Gerber, Soderberg, and Goodman line. Thank you.